Welcome to this presentation on our recent paper on gravitational wave from current cosmic strings. My name is Pierre Auclair. I'm a postdoc at UC Louvain in Belgium, and we carried this work with Simone, who's a postdoc at the VUB in Brussels, with Vedran, who's a postdoc at the Northwestern University, and Kai, who's a professor at Münster University. In this work, we are interested in cosmic strings that may arise from cosmological quantization, and the detection of such objects would clearly point towards new physics beyond the new standard model. The gravitational wave signal of a string network has been studied for a long time, and is dominated by the emission of closed string loops, which are formed when the long strings intersect themselves and chop these loops off. Strings, it's known also that they may have currents in them, and in particular we focus on chiral currents here, that may modify the dynamics. And to study that, we use the CVOS, so the current velocity one-scale model, which models how the long strings evolve with a current in them. And we use that to take into account the evolution of the current and then the loop number density and the different observables. So the CVOS is this set of equations that we've rewritten a little bit, with t, the cosmic time, and the scale factor, which is a certain power law of time, with this parameter mu. Alpha is the scaling correlation length, so the correlation length divided by time, and y is a measure of the current strength on the strings. So you can write this set of equations as the following with respect to log time, and in which case the right-hand side does not depend on absolute time. So what you have here is an autonomous system that you can evolve irrespective of time. So if you have a set of initial conditions in this box on the right-hand side and you let it evolve, what you see is this. So all the blue dots are the initial conditions that fall into this attractor on the y equals to 0 plane, which is the standard Nambu Goto attractor in which alpha is scaling, meaning that alpha and v are constant. Then you have this other attractor in red, which is along this black line, in which alpha and v go to 0 and y remains high, close to 1. So you can try to understand what happens here by simplifying a little bit this autonomous system by assuming that alpha and v are very small and that epsilon, which is basically 1 minus y, is also very small. So from the third equation, the requirement that epsilon and its derivative are small tells you that v and alpha are proportional one to another at the first order with this proportionality constant kappa. We can use that and simplify the first equation, and you see that alpha is basically a power law with respect to time, with an exponent, delta, which is given on the right-hand side. Then, since v and alpha are proportional one to another, you can, you know as well that v is equal, that v is a power law, and satisfy this equation, in which case you can equate epsilon in the second equation with here delta kappa. What you obtain is that epsilon goes like alpha squared and is also a power law. So from this very simple approach, you see that the steady current attractor goes like a power law, and you require that for consistency, delta is negative. So if you take this delta and you set it negative, what you obtain is an upper bound on the on nu, which tells you how the scale factor goes with respect to time. So in radiation era, nu equals to 1/2, in which case this attractor exists, but it's not the same in matter era, because there the parameter nu is 2/3, and then you only recover the standard Nambu Goto attractor. So this steady current attractor is bound to only live for a certain amount of time in the universe. It cannot go until today. Now we can calculate the loop number density itself, and we use an energy conservation argument. So we calculate the energy lost by the network. So this is given by the CVOS model. And we say that part of this energy is received by large loops, where P here is the loop production function. Assuming that the loops are all produced at the same size, alpha t, basically, we can normalize this production function with this coefficient here. And from that, we can calculate the loop number density itself with this simple equation. So this simple equation actually hides some subtleties in this t star variable. And this t star variable is defined as the following. You take a certain loop, and you look back in time, and you calculate the time at which it was formed. So this is t star. In practice, it's a little bit difficult to calculate, but once you have it, you can express the loop number density very simply. So how it evolves, so you see this animation on the right-hand side. If you have no current on the network, then the loop number density is scaling, meaning that if you normalize it properly with time, it does not evolve. Now we put a current in and we let it evolve for a little bit, and what we observe is this. So alpha goes to 0, so meaning that you form smaller and smaller loops, but you form them more and more numerous. Then all the scales are increased, and at some point this current disappears, either because of leakage or because you have entered matter here. When it disappears, the dynamics of the network is not very well known, and we make the conservative assumption that the network recovers the standard Nambu scaling instantly, meaning that you at one time you form very small loops because alpha close to 0, and then at instantaneously you form loops that are very large. So you have a gap in your loop distribution, as you see here. And then you let it evolve again, and you recover the standard scaling distribution. We can use this loop distribution and calculate the stochastic gravitational wave background, and it has 3 different contributions. The first is from the loop that are formed before the appearance of the current. Then you have the loops that we just talked about that are formed during the current carrying phase. And then you recover the standard number density. So the first and the third one are very well known, and the second is our new result. And as you see on this plot here, it's what gives this bump here, because we form more and more loops that emit a lot of gravitational waves. So you see that if you want to explain the gravitational wave power spectrum in nanograph, you need a g mu, so the string tension, to be 10 to the minus 11. But in this case, you don't observe anything in LIGO-Virgo Cagra detectors. However, if you have a current, a steady current attractor, as this, that lasts for a certain amount of time, then you can have this bump that produces observable signatures in LBK. So this is what we constrain on the next slide. So we set g mu 10 to the minus 11. We say that there is this steady current attractor for a limited amount of time between t ini and t end, and we calculate the stochastic background at 20 Hz. We have constraints from LBK, the O3 run, that tells you that this quantity cannot be as large as you want. And this sets constraint on this 2-dimensional plot. Okay, now I've reached my conclusion. So we went beyond the standard Nambu approximation for cosmic strings by including additional world-shaped degrees of freedom, in particular chiral currents and the strings. For that, we used the CDOS, so current velocity one-scale model of Martin and his collaborators from last year, and we identified 2 different attractor solutions, in particular a non-scaling attractor in which the currents remain high. This results in a growing energy density in long strings that translate into a growing energy density in loops and eventually in gravitational waves that we have calculated and constrained with LBK. Thank you for your attention and have a nice day.